afternoon session. And our first speaker is Pietro Speziali. We talk in title on the classicality of the Artin-Mumford curve. Pietro.
Thank you, Lucas, for a very nice introduction. Good afternoon, everybody. First of all, I would like to thank the organizers for giving the opportunity to be here. It's a pleasure to be in São Carlos after so many years, seeing some friends I haven't seen in a while, so it's been really nice. It's always nice to be back here. This is one of the places I call home. I really enjoyed my time here as a postdoc, and I mean, it's always nice. So this is a joint work with my PhD student, well, technically former PhD student, Lina Isabel Trevino Vieira from Unicamp, and Eric Rojas. Eric is, I think he's now already in UFRJ, but at the time he was a postdoc in Unicamp with us. And also I would like to thank FAPESP for the financial support and for being here. So, in a way, I'm sorry, I have a terrible handwriting, but the best way I have to function is giving chalk talks. I'm sorry. I think it comes with residency in a way. I think it's an unconscious way to pay homage to a dear friend who used to be in Campinas and is not with us anymore, and used to give chalk talks. So very briefly, what it is talk about. Let me introduce the main persona we have, which is the so-called Artin-Mumford curve. So fix K, an algebraically closed field of characteristic P, bigger than 0. So you can think of the Artin-Mumford curve is defined as the normalization of the curve whose function field is given by x to the p minus x, y to the p minus y equal 1. So you may think, okay, why should anybody be interested in this kind of curve? Of course, you may replace here this one with a c, say, in fp square, but all the curves are isomorphic. So since I'm interested in a birational point of view of everything, basically when I say algebraic curve, you can think you always have to mean a projective non-singular curve or an algebraic function field. So this is what we're thinking about. But this curve has a long history of reasons of being interesting. Why is that so? So if you know that since we are working on algebraically closed field of passive characteristic, the Hurwitz bound 84 G minus 1 does not hold in general, but it holds for the so-called tame subgroups. So for a while, and of course you have lots of examples of curves with many automorphism groups. What does many mean in this case? Of course, you know that you have the Hermitian curve. Well, basically what you know is that there is just one curve with more than, say, 16 g to the 4th automorphisms. You have like 4 curves with more than 8 g to the cube. And then things start to get messy. But all of these curves have P rank 0. So what does P rank 0 mean? Well, you have many ways. Of course, one should introduce, in this case, the P rank. When you have curves in characteristic P, the picture of birational invariance of the curve gets richer. Of course, you always have the genus of the curve. And who is the P rank? Well, you may think of the P rank in several ways. My favorite one is maybe the following. You have to count the number of independent. So the P rank of a curve is the number of independent unramified Galois P extensions. the function field k of x. This is equivalent to counting p torsion point on the Jacobian of the curve. What about the Artin-Mumford curve? So the genus of x is p minus 1 square, and gamma of x equals the genus is also p minus 1 square. In the 80s, the Artin-Mumford curve in 84 appeared in a paper by Doré-Subrau, which explained why the name Mumford appears, because in thesis this is an Artin-Schreier curve. Why? Because its function field is a double, well, it's an Artin-Schreier extension of k of y and of k of x as well. But at the time that Mumford made the question, is it true? So all the known examples at the time, of course, with too many automorphisms, so more than the Hurwitz bound, had p rank 0, so no p torsion on the Jacobian. And Mumford asked for examples of curves with too many automorphisms, which were also ordinary. And Doré-Subrau, in his PhD thesis, gave a positive answer, the answer given by the Artin-Mumford curve. Why? Because here's, of course, you say, so I said automorphisms without giving too much context. In this case, what you can think of automorphism, what is the automorphism group of X? Is the automorphism group of the function field k of x fixing the base field pointwise. So here, since we have a very nice plane equation, we have a nice way of visualizing this kind of automorphism groups. Because of course, if you take them up, say, tau of x and y equal x plus alpha y, or alpha in FP, well, of course, it can be not, to generate, it can be in FP, say. This is an isomorphism group, this call it tau 1, tau 2 of x and y, x, y plus beta, say. Also, you have sigma of x and y. So because this is very symmetric, you can switch x and y in the function field. So sigma x of y, yx is also an automorphism group. Also, to complete the picture, you send xy in dx 1 over the y, this time is in fp square, in fp star, sorry, non-zero element. So all these maps are in the automorphism group. They actually generate a group of order p square, p minus 1 times 2, and this happened to be the full automorphism group of X. So for p bigger than 41, this exceeds 84g minus 1. And so here you have, there you go, your automorphism, your example of an ordinary curve, ordinary, which means in this case, genus equals the p rank, with too many automorphisms. I should also mention that most of the known ordinary curves with too many automorphisms, here you see this is roughly genus to the 3 over 2. Most of the known examples of curves with too many automorphism groups which happen to be ordinary have roughly this size of automorphism. There is also a very nice result by Zarakeli and Korchmaros in 2015, which tells you that actually if you have a curve with genus, an ordinary curve with genus p minus q square and out x isomorphic to this guy, because this guy is actually, you have elementary abelian group of order p square, semi-direct product with a dihedral group of order p minus 1. And with this kind of automorphism group, then actually your curve has to be isomorphic to the Artin-Mumford curve. So there are many ways for which one should be interested in this kind of curve. There is also another thing that makes you wonder. I mean, that there is another reason of interest of this curve, which is the following, which will lead you, because up to now I have said nothing about classicality. I have never said, even say what I mean by classicality. But that will be factored in a minute. So, take, for instance, the Fermat curve of degree n. Similarities that these two guys shares. Here you have these two distinct subfields, which are Kummer extension, which are Kummer subfields of order n, and here you have two which have a degree p. Actually, the Artin-Manford curve is one of the fewest. I mean, in general, if you have you may pose the kind of problem. Assume that I have a curve whose function field is given by a Galois extension of the cyclic Galois extension degree p of a rational function field. How many other Galois subfields order p cyclic do I have? Generally speaking, one, exactly one. The Artin-Manford curve happens to be one of the few selected guys which has two. Actually, it has, I think it's the only one that has exactly two, because the other ones have so many more. So still, you have this kind of symmetry. Also here, you know that the automorphism group is isomorphic. Well, when this n is not different from q plus 1, which is power of the characteristic. The automorphism group here is isomorphic to direct product of Cn times Cn times S3, so the symmetric group on 3 elements. So you sort of see some more possibilities. One thing that I would like to highlight is also that you both share this linear involution. They happen to have the same linear involution as automorphism. And so why am I interested in that? So to each point, of course, if I guess many people here like codes, in particular GOPA codes, and you know that in many cases you do GOPA codes on algebraic curves, the so-called one-point codes. So you take a point, you have the Weierstrass semigroup associated to the point, and then you construct via Riemann-Roch spaces. So to any point on algebraic curve, you associated the so-called gap sequence at P, which is a sequence of integers, say L1, L2, LG. How are these described? Well, these are actually the complementary of then 0 minus the Weierstrass semigroup at the point, or otherwise, you can see it is linked to take a basis of holomorphic differential, which happen to be actually G. And so you have that, say, I belongs to G of P, if and only if I plus 1 is the vanishing order at P of a holomorphic differential. So it is natural when you have a nice curve to study gap sequence at the points. But what happens if you work in characteristic 0? Then for any curve, this generic at a generic point, GP is actually 1 G. So you have the set of Weierstrass points, which has a set of points such that P is different. G of P is different from 1 blah 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 G. But this is in characteristic 0. When the characteristic is P, which is the thing that we are interested, this is true. If this is the case, we say that X is ordinary or classical. But this might not be the case. When the genus is small, but to G minus 2, when the characteristic is small, ou seja, smaller than 2g minus 2, then the curve might be non-classical. What does it mean? It means that at a generic point, you may have a different sequence. So the question, this is a question that my advisor, Professor Kochmarz, made me a long time ago and asked me, is it true that the Artin-Mumford curve is classical, in the sense that does it have the classical gap sequence? I will tell you. So our work revolved around answering this question, and inspired by the similarity with the Fermat curve, why not? While we were at it, say if the points which are fixed by this involution are Weierstrass points, and compute their gap sequence. So a little spoiler here, if p equals 3, actually x, the Artin-Mumford curve, is classical with respect to the canonical series. And here, well, we don't have to, we didn't really have to do anything, actually, because this has been known in the literature for a while, a posteriori, because there is no non-classical curve of genus 4 in characteristic 3. So this is a very nice result dating back to the 80s. For p equals 5, or well, hey, for p bigger than 3. So what you might do, what you might think of doing is, for instance, computing the gap sequence at some points in which you have some more control on the things you want to say, and or more control of the geometry, and then apply some criteria which basically date back to Sorbolok theory to decide if the curve is classical or not. And then you can say that these points are Weierstrass. So in a sense, it all revolves around how do you compute gaps at those points. We try to use two different strategies, and which are related but somewhat different. One interesting thing is the following. You have, so if you take the Artin-Mumford curve, it has 3 short orbits of points. So that is to say, the automorphism group acts fixed in some points. Here you have, say, points at infinity, because the 2 points at infinity are centered of 2 each of p rational branches, and those points you can know anything you want to by using Artin-Schreier theory. And then you have 2 orbits of p minus 1 square, sorry, p square p minus 1, p square p minus 1 points, which happens to be fixed by involutions. Also, these points are the set of points which are the so-called sextatic points. What does it mean? It means that they have a higher order of contact with conics. You have the inflectional, if you have a plane curve, have the inflection points are the ones with an unusually high tangency with the tangent. Sorry? So you have the osculating conic, which is the tangent of conics, and it's in this case, these points are Weierstrass in this sense. So actually, the order of contact with the conic is p plus 1, and the generic point is p. So what we did in this sense was make a very geometric construction. So what you want to do is construct a holomorphic differential. So in a way, a natural way of doing that, always done, is to use function that you can control. So we construct quite a number of gaps simply by considering, say that Cp is the osculating conic at the point, multiply by z, which z is this kind of function. It is if the point is a, b1, z is y minus b x minus a to the, say, to the u to the v over x to the p minus x. You do take the differential z times cp over, sorry, d of x, and you see that this gives you a holomorphic, a positive divisor. So it takes the point p here, and then here you have a nice way of controlling a lot of the points, a lot of the values. For p equal 5, these are enough to conclude that the curve is actually classical, and these are Weierstrass points. For p bigger than 5, and I'm done, This is still open. We're trying to use different techniques. Actually, the dream is either to determine a subset of gaps which is big enough to say the curve is classical or not, or complete them all. So this is pretty much all I wanted to say. So I thank you very much for your kind attention.
Okay, thank you, Pietro. Do we have questions?
Not a question, it's a comment. I love Cholt talk, so thank you so much.
Thank you. Sorry about the handwriting. This is something I should have.
Do you know about the classicality of the linear systems of degree 1, 2, 3, and so on?
So what we did is use the non-classicality with respect to conics. With lines, I think, I'm pretty sure it's classical. And another way it would be, the next natural step would be to study, for instance, its classicality with respect to cubics and see if the osculating cubic can help us, for instance. That would be the natural step, but still haven't got back to that.
Okay, more questions? Yeah, I have one silly. At the very beginning, you just have the equation, right, for the Artin-Mumford. Do we know the number of rational points for every extension of FP?
So for every extension, not, but this is a nice thing. So actually something I wanted to say. So the automorphism group is defined over FP. So in this, so all the sets of rational points are unions of orbits, right? So if you take the FP rational points, they are 2p points, which are just like the points here at infinity in these two ordinary singularities. Then you have one of the two orbits, which is a set of FP square rational points, which are not FP. The other short orbit are the F to the P, FP to the P rational point, which are not FP square. With Erivelto and Nazar, we did some computation some time ago. I don't remember. I think we computed FP cube. I think there are no more FP to the fourth.
No, yeah, it's just because from the equation, it's basically writing an element as the product of two elements with zero trace, right? So
yeah. Yeah.
Oh, okay. No, okay.
I mean, like there is one other thing that you could try and use is the fact that actually, because here, I mean, you have, if you see, you have this automorphism group, which is isomorphic to ZP times ZP, so you have actually P plus 1 subfields. So P plus 1 subgroups. P minus 1 of those have no rational quotients, and you kind of know, for elliptic curves, you kind of know a lot of the deal about them. So you can sort of think of using them like to compute the zeta function.
Okay, so let's thank the speaker again. Okay, so our next speaker is Stephen Wan from Carleton University, and he's gonna talk about the classification of permutation binomials of the form x to the k plus ax over f2 to the n.
Thank you,
Stephen.
Lucas. So first, I want to thank organizers, in particular Hereto, for organizing such a wonderful conference. I have been enjoying so far, and I expect more, right? Thank you. So I'm going to talk about the classification of permutation binomials over finite fields of even characteristic. So FQ, finite fields of Q elements, FQ star contains all the non-zero elements. A polynomial with coefficient in FQ is called a permutation polynomial, or PP, if the induced mapping from x to f of x is bijection, right? So it's well known that monomial x to the k is a PP of FQ if and only if k is relatively prime to q minus 1. So the map x to the k maps 0 to 0. And then if you consider the cyclic group of non-zero elements, because it's cyclic, so x to k permutes a cyclic group if and only if relatively prime to the size of the group, which is q minus 1. So permutation polynomial have been studied a lot, even binomials since 60s by lots of famous people like Carlis Wells, Ritter, Robinson, Daqing Wan, and many of you here. So I cannot list all the names, so I refer Xiangdong Ho's survey for a start. Okay. So I took a different perspective on binomials, so which also mentioned by Seham's beautiful talk yesterday. So cyclotomic mappings. So if I look at a binomial, so I factor out x to the r, so I have x to the k minus r plus a. And then I take the greatest common divisor of k minus r with the q minus 1. So I call this s. So L as q minus 1 divided s, I call this parameter as index of polynomial. Okay. So in this way, I can rewrite my binomial as x to the r times x to e s plus a. Or if I call this h of x is x to e plus a, then I can write the polynomial as x to r h of x to s. So this process works for binomial. Of course, it works for polynomial as well. Okay, general polynomial. So by writing polynomial in this way, I can think a polynomial as a cyclotomic mapping, which is a monomial in each coset. So it becomes much simpler mapping in each coset. So finite field FQ star is a cyclic group generated by gamma. So if I take a subgroup with the index L, so generated by gamma to the L, so I call this C0. Then we have L cosets, right, called C0 up to CQ. So in each coset, so this x to the s actually maps all the elements in the coset as a constant. This constant actually is h of zeta to the I. So the polynomial actually behaves like a binomial, a monomial in each coset. So those A0, AI, and AL minus 1 are constants. So to study permutation, so of course, monomial, you need to study monomial permutes cosets. So eventually it reduces, R has to be relatively prime to the size of the group. So R as relatively prime. And then the monomial maps a coset to a coset. So in order to be a permutation of the whole finite field, you need to permute all the cosets. So in fact, you would have the following picture. So if you consider a polynomial of this form, so you take a projection x to s, you make a commutative diagram. So f bar is x to r, h of x. So you can reduce the permutation polynomial as a permutation of roots of L's roots of unity. And if you look at each fiber, right, so take the pre-image of those elements in the roots of unity, so the polynomial behaves like a monomial. So that's the monomial in the cyclotomic mapping. So therefore, you have this simple criterion, like R and S relatively prime, and F bar permutes roots of unity. So this criterion has been studied by many different people in different forms. I listed a few here. there are so many applications in studying permutation polynomials. So in particular, if for the binomial, so because 0 map to 0, so this one has to be non-zero, so S cannot be 1. So which index cannot be, q minus 1. In particular, this minus a to the L cannot be 1. Okay. Now, so here is a way, based on the previous description, here is a way to generate all the permutation polynomials with a given index. Okay, so basically you do 2 steps. First, you determine all the cyclotomic PPs. So you can choose those constants in front of monomial by taking any permutation of ZL and then integer, t. So you can generate all those constants AI. Once you have those AI, and then you can find the coefficients of polynomial, those BL minus 1, BL minus 2, B1, B2, by solving this system of linear equations, h of Zi equals A. So basically, that's the inverse discrete Fourier transform. You can do that. So you basically solve this system of linear equation. You can find all the permutation polynomials of any given index. If you are interested in binomial, so basically means you want to find a solution such that the 2 values are non-zero. Okay. So here's a quick summary of index view of permutation polynomials. So for any given index, as long as the size of field is large enough, then you can always find the permutation binomial of that index. So that's actually a result of Carlis-Wells, 1962. It's not given in the language of index, but the result is there. And the smaller index, the easier to find all the permutation binomials. From the previous system of linear equations, you can see that, right? The smaller index, the smaller matrix, so you can find all the permutation binomials quicker. And over prime field, by a sequence of work by Wan, Tengwa, Masuda, Ziv, so you can see that the index of permutation binomial over prime field always bounded by square root of p plus 1. So the classic question is, how can we classify permutation polynomials or binomials in terms of index? So this talk actually, we try to do that. But before do that, I recall a few binomial results over the extension field. So the first result is the Ziv result on this type of binomial, R x to the e times q minus 1 plus a over fq squared, under the assumption that a to the q plus 1 is 1. So in this case, the index actually is q plus 1 over e, because here, because of this result, e cannot be relatively prime to q plus 1. And Ho and Napano, they studied the few polynomials without this assumption. So basically, index is still q plus 1 over e, but e is 2, 3, 5, 7. Okay, and then later on, Ho also showed that for any prime e, without this assumption, which means a to the q plus 1 is not 1, there are only finite many pairs, q and e, such that this is a permutation binomial. So later on, Li, Chu, Chen, they also classified this type of permutation binomials on the assumption that R is in this range. So basically, this class of binomials has index q plus 1. And those are the binomials over q squared. So Masuda, Rubio, Santiago, actually, they studied the binomials over fq to the n for n between 2 and 4. And also, q is prime such that n is 5 and 7. So those permutation binomials have index very big, q to the n minus 1 plus q plus 1. Excuse me. So I'm interested, this talk is about permutation binomial over even characteristic. So it's observed that permutation binomial, most of the permutation binomials are obtained from composition of binomial with this exponent 1 with monomials. Okay, if you do the test, most of them are generated in this way. And one of them, so that's why we focus on this type first. It basically covers most permutation binomials, although we haven't proved yet. So another one is if this k is a prime power, like a p to the k, p to I, then it's called a linearized binomial. So linearized binomial, because it's linear transformation, so it's a permutation if and only if the only root is 0, and it maps 0 to 0, so which means you want a non-zero part, x to the p I minus 1 plus a is non-zero, so you can easily characterize it. So linearized permutation binomial is done. So in this talk, we just focus on non-linearized permutation binomial of this form, okay? And one of the earlier results did by Masuda, Daniel, and myself is when we consider q minus 1 is a Mersenne prime. In this case, we show there's no permutation binomial over fq, okay? For example, if q is 2 to the 5 or q to the 7, so q to the 5 minus 1, q to the 7 minus 1 are both Mersenne primes. So you cannot have permutation binomials over it. So then what we did is we did exhaustive search over 2 to the n for n up to 12. Okay. So and then we focus on non-linearized because linearized is easy. So the first example, we can find the non-linearized permutation binomial is over f2 to the 6 because f2 to the 5 doesn't have it. Before that, you have linearized. So we can find all the degrees in this case, and we compute all the indices, right? 3 and 7 in these cases. Some of those examples are covered by previous classes listed in the table, but the others are not. So in this talk, I show you 3 more new classes, which basically explains all those permutation binomials. So the next one, because we don't have permutation binomials over 2 to the 7, so the next one is 2 to the 8. Again, so you can see that the index are very small, like 3 and 5. 2 to the 9, the index are 7s, okay? And 2 to the 10. So here, the largest index is 31, which is actually smaller than the square root of 2 to the 10, because 2 to the 5 is 32. So again, it seems like even over the extension field, you may wonder whether non-linearized permutation binomial has relatively smaller index, right? But it's not true. So there's no permutation binomial over 2 to the 11. And then the next one, over 2 to the 12, so we found all those degrees and indices. It turns out there are 3 permutation binomials have index 91, which are bigger than the square root of q. Okay, so 3 of them, 2 in the bold letters, 1 in the red letter. Okay. So based on those data, we actually constructed 3 new classes of permutation binomials. So the first class is over, again, like many people have studied, right, over fq squared. So, but we have index q plus 1 over 3. So this is when n is greater than 3 is odd. And then the polynomial has this form, x to the 6q minus 5 plus ax. And the characterization is very simple. There's a sporadic case when n is 3, but when n is bigger, then the condition is a belongs to the mu q plus 1, the root of unity of q plus 1, but does not belong to mu q plus 1 over 3. So here, you notice that here the exponent, we have 6q minus 1 plus 1, 6q minus 5, right? So unlike host result, they consider primes, like a 2, 3, 5, 7. So this is the first example, you have composite number. So it covers the permutation binomial of these 2 in our table, but it's infinite class. Okay. So I quickly tell you the idea, proof idea, right? So one direction, we use this community diagram. This is standard technique. So if you want to study the permutation polynomial of fq squared, so you just reduce this one to the root of unity, so like this. And then under the condition we had, like A belongs to root of unity, doesn't belong to the mu q plus 1/3. So this expression inside the bracket has no root in root of unity. In this way, you can rewrite this one as a fractional function, rational function. And then you apply the standard trick and they reduce it to monomial. Once you reduce monomial, it's easy to characterize when it's a permutation. So that's one direction. So the other direction, again, is a standard technique, Hermite's criterion. To find the condition for A, so we basically, we want to compute, we want to make sure a power of the polynomial, the coefficient of x to the q minus 1 in this power is 0. That's the Hermite's criterion, requires all the powers, doesn't have degree q minus 1. So we compute this coefficient. Basically, you need to solve all the possible solutions. So we explicitly find all the possible, use p-adic analysis. We found all the possible solutions and then obtain some equation in terms of A. So you find the condition for A. Okay. So that's basically the proof. And the second result is over Fq to the cubed. So this one index Q squared plus Q plus 1/3. So the index is bigger than the square root of Q, Q cubed, right? So it covers the examples like over F to the 6, these two examples. But the polynomial has this format, x to the q squared plus q/2 plus ax for n even, okay? Again, the characterization is very similar. So it does not, so the index is this, right? A cannot belong to mu L, but A belongs to a multiple of index, 3 times L, okay? The proof also use Hermite's criterion using a different power. This is a T, and the multivariate method for another direction. So what is multivariate method? So basically, you want to solve this equation. So f2x equals b for any b. So you want to show that there's only a unique solution. But normally, this is high degree polynomial equation. So what you can do is you replace x to the cube by y to the cube by z. So you can convert a high degree equation into a system of equations in terms of x, y, z, 3 variables, by low degree, so you can solve it. So that's the idea. And then notice that this q squared plus q plus over 2 is relatively prime to q cubed minus 1. So you can find the inverse of it. And then you take the composition with a monomial and monic, and then you can get another permutation binomial for free. So basically, we obtain 2 classes of permutation binomial with a relatively large index q squared plus q plus 1/3. So we could not explain the third one. Okay, so that covers 2 of those 91. Okay. So the last class is over Fq to the 4th with index q plus 1, and so the degree is this. Q cubed minus q squared plus q minus 1/2 plus 1. And the condition is very similar as well. It's in the mu q squared minus 1 doesn't belong to mu q plus 1. The proof idea use, again, AGW, but more involved, and the rational permutation function of degree 2. So basically, again, it's using kind of a commutative diagram. But in order to simplify discussion, we take the composition of F3 with x squared. So then we reduce this one to roots of unity. But then the extra effort is we take a first order rational function. We convert the permutation of roots of unity to permutation of the projective plane. But here becomes a rational function. But its rational function has degree 2, which has been classified. So we can use this classification to get permutation binomial. Okay. So basically, we have basically constructed 3 new classes of permutation binomials, and we can explain all the PPs for n less than or equal to 8. So of course, it's very natural to ask, what about the general n, right? And to solve this problem, there are 2 concrete questions. So why there's no permutation binomial over 2 to the 11? 2 to the 11 minus 1 is not Mersenne prime. But we don't know why this is, there's no permutation binomial. And also, how do you explain the third permutation binomial of index 91 over F2 to the 12? So finally, of course, we would like completely solve the problem for any binomial with this exponent. Although we tested over 2 to the 10 or 2 to the 12, there's no permutation binomial which are not obtained from this type with monomial. But we don't know how to prove, or we don't have counterexample either. Okay, so I thank you for your attention.
Thank you, Stephen. Do we have questions?
Yes, see him.
Thank you so much. Super results, method, and very nice talk.
Thank
Excellent results. Yes, I have a question. Do you think interesting to find the explicit the compositional inverse? I mean, and the second question is it? I mean, for future work. I mean, this is a very nice classification. Sometimes we need the expression of the inverse. Yes, so
Yeah.
do you think it's interesting or not? And the second is about involutions. Yeah.
Thank you. Yeah, for the inverse for this type, we have a general way to find the general expression because everything is x to r, h of x to s, right? So it's reduced to find that the inverse of the roots of unity. So we need to find the inverse of this, essentially, or inverse of that. For many classes, we are able to do it, but not, of course, not every. But we can do some. Again, the involution question is very interesting because it has a lot of application. I know I have been aware of your work, those things.
The question: do you think that is because we in crypto for applications? It's interesting to have to generalize evolution, which is hard. I mean, there is very few evolutions, yeah, and so do you think this it's interesting or not to study those who are?
Of course, it's very interesting to study
Okay,
this. Actually, I have been thinking. I recently wrote the survey for inverse because the involution is so important. So actually, I'm thinking to do something along that line for involution.
Okay.
We can discuss.
Yes.
Yeah.
Anyway, it's really very nice results. Yes.
Thank you.
Congratulations. It's very nice.
Thank you.
Okay, I think we don't have time for more questions. So if you have any question, you can ask Stephen.
Thank you.
So let's thank the speaker again. Okay, hello everyone. Welcome back to this afternoon session. And so in the second part, the first speaker is Said Tafazolian from University of Campinas. And he's going to talk about the maximality of hyperelliptic curves defined by Chebyshev polynomials.
Thanks. Agora tá certo? Tá. Thanks. First of all, I would like to thank the organizer of this conference. I want to speak about the maximality of hyperelliptic curves. First of all, I start with some notation. The curve, by the curve I mean a projective non-singular algebraic curve. And I consider the curves defined over some finite field. And if we consider some extension of a finite field, we can define the zeta function of curve over the field k. We consider the exponential function of the number of rational point of the curve over kn, some extension of a finite field of degree n. And we know that by rationality of zeta function, we know that we have some polynomial of degree 2g with integer coefficient. This polynomial is called L polynomial of curve. And by the Hasse-Weil theorem, we know that we have some bound for the number of rational points of a curve. And if a curve attains this upper bound, we call the curve maximal over this finite field. And by theorem of Tate, we know that a curve is maximal over Fq squared if and only if L polynomial of a curve has this form. And okay, but there are many methods to construct maximal curves because we need an explicit equation of a maximal curve in coding theory. For example, one of the famous one is based on this result of Tate there. That say that if we have some morphism between two curves, the L polynomial of the second curve divides the L polynomial of C. Is that mean if we have some maximal curve, any subcover of that curve is also maximal. And for example, if we consider this Hermitian curve, this Hermitian curve is maximal over Fq squared. It's very easy to show that by counting the number of rational points that this curve is maximal over Fq squared, and so any quotient of this curve is also maximal over Fq squared. And many of known maximal curve are covered by this Hermitian curve, but also we have several that does not covered by this curve. Is not important. There are many methods to construct of maximal curves, but today I'm interested to introduce a new one for constructing maximal curves. First of all, I need to explain some argument that we need to explain how we can to show that a curve is maximal. One of them is a p-adic Newton polygon of a curve. I mean, a p-adic Newton polygon of a curve. I mean, the Newton polygon is based. I mean, is related to p-divisible group of associated to Jacobian of curve. But here I have considered some equivalent definition for Newton polygon of curve defined over finite field. If we consider the L polynomial of the curve, we can consider this point in the plane, and the normalized p-adic Newton polygon is defined to be the lower convex hull of this sequence of points. And I mean, this Newton polygon is a geometric has a geometric property. I mean, is not dependent of the finite field. And for example, for elliptic curve, we have two possibilities. The first one is a Newton polygon of the some ordinary elliptic curve, and the second one is the Newton polygon of supersingular elliptic curve. You know, the supersingular elliptic curves, that means the one elliptic curve with no p-torsion point. Okay, if we have a curve with that the Newton polygon has all slope is called half. This curve is called supersingular as a same as for the elliptic curve. And the second one is called the supersingular elliptic curve. And this is equivalent to say that the Jacobian of a curve is isogenous to product of the some supersingular elliptic curve. And it's very easy to show that if we have a maximal curve over some extension of the Fp, then all the slope of the Newton polygon are equal to half. That means all maximal curves are supersingular. And you can see that the maximal curves have the interesting geometric properties because all of them are supersingular. Okay. Today, I want to explain some maximality of some family of curve defined by Dixon polynomials of the first kind. But here we consider the parameter equal 1, and we call this family of polynomial Chebyshev polynomial. And the Chebyshev polynomial recursively defined by this relation and also characterized by this property. And for example, I have written some example of Chebyshev polynomial. You can see for a small degree, all of them has the few terms and are simple, but if we consider some degree of, for example, 16 or 17, we have many terms. And if we want to consider the roots of this polynomial, or I mean the rational point of the curve defined by this polynomial is out of received by. Okay, and we can see that the Chebyshev polynomial of degree odd are odd, and of degree even are even. Is that mean that we need to study separately both of them? Okay, it is easy to show that with some condition, this curve is covered by Hermitian curve, and so this curve with this property is maximal. It's not difficult, but we can also to show that, for example, this non-singular plane curve is maximal over Fq squared if and only if 2n divides q plus 1. Does that mean if we have some curve of a finite field, maybe it's simple to find some necessary condition for maximality, but the other side sometimes it's not easy. I mean, to find all finite field that a curve can be maximal over them. But today I want to consider hypereptic curve defined by some Chebyshev polynomial of degree d. And the aim of this work is to characterize the pairs Q and D such that this hypereptic curve is maximal over the finite field Fq squared. And as I say, it depends on D is odd or is even. And also, it's very interesting that we have is depend of the P. If P is 1 mod 4 or 3 mod 4, all of the result is totally or completely different. In the first one, when the P is minus 1 mod 4 and D is even, we need some auxiliary curves, and we can consider the curve X and the elliptic curve E. You can see that this equation of this hypereptic curve is simple, and we can apply several arguments to control or to classify maximality of the curve X and the elliptic curve E. But for the curve C, it's not possible to apply several arguments, for example, Cartier operator or Weierstrass point theory. Many arguments we cannot apply for the curve C, but using these auxiliary curves, we can show that the Jacobian of the curve X is isogenous to the Jacobian square of the curve C multiple elliptic curve E. And using this isogenous, we can find some equivalent for maximality of the curve C and the curve X, and we can classify instead of the curve C, the curve X, and also for the D is odd, we need more curves, but with the same argument, we can find some decomposition for the Jacobian of the curve X to find some, to classify the maximality of the curve C. And we can see that when P is -1 mod 4, depend on the D is even or D is odd, we have some classification for maximality of these curves. But today, I'm interested to speak about this case. P is 1 mod 4. In this case, unfortunately, we couldn't use the similar argument to find some necessary condition for maximality of this curve. I mean, we could not show that this curve in this case is covered by the Hermitian curve. But using the magma, we have found some maximal curves in this condition. And we start here only the degree is some prime number. You know that using this property for Chebyshev polynomial, we need to consider these curves where L is some prime number. Okay, first of all, I mean, in this case, when P is 1 mod 4, first we consider L is -1 mod 4. And we can show that in this case, there is no any maximal curve of any finite field of characteristic P. How we can show this? Using the supersingularity of curve. I mean, we can determine the Newton polygon of these curves in this case, and we can show that there is some slope different of half, and so this curve is not supersingular. But how we can determine the Newton polygon of the curve? It's not easy to determine the Newton polygon of any curve. But this curve is very interesting. I mean, in this case, we could find some CM field in its endomorphism algebra of the Jacobian of the curve. I mean, we can show that the Jacobian of this hypertrophic curve is a CM abelian variety. And for CM abelian variety, based on the work of Shimura and Taniyama, one can describe at any prime the Newton polygon. I mean, all slope of the Newton polygon of abelian variety with complex multiplication. So we need first to show that the Jacobian of these curves is CM abelian variety, and after using some known argument, one can determine the all slope of Newton polygon of this hypertrophic curve. Okay, for the if P is 1 mod 4 and the L is -1 mod 4, there is no maximal curves. But if P1 and L also 1 mod 4, we want to study or to find some condition for maximality of the curve. And the theorem say that if P is L primitive, then this hypertrophic curve is maximal over this extension of finite field. I mean, L -1 is exactly 2G. I mean, the G is the genus of this hypertrophic curve. And I want primitive. Does that mean? exactly. I mean, the first degree of P when is p power k mod L is 1 is exactly L minus 1. Exactly. Okay. I want to show that how we can prove this theorem. First of all, we know that the Dixon polynomial with this condition is a permutation polynomial over Fq. And so, as I say that P is L primitive, I mean, satisfy this equivalent condition, so we know that for any K is not it's not bigger of L minus 1. The Chebyshev polynomial is a permutation polynomial, and so the number of rational points over Fp to K is exactly 1 plus P to K. Okay, using some idea that I learned in the paper of the Professor Uzdubak, we can, using this property of the coefficient of L polynomial, we can show that most of all, this coefficient of L polynomial is 0. Here G is a genus, and L minus 1 over 2 is a genus. So all coefficient using that the first one, SR, is exactly the number of rational points over some extension of degree R of Fp. You can see that the all coefficient of L polynomial is 0. Okay, it's in this case, with this condition, the L polynomial of the curve is equal in this form. But using that using that to say that P is L primitive, we can see the curve is supersingular. Is that mean P to G over 2 divides N? Okay. So as using that the P is L primitive, we can determine the all slope of the Newton polygon, and we can show that the curve is a supersingular. For supersingularity, we need that this number divides the N. Okay, does that mean the characteristic polynomial of the Frobenius applying the heterocohomology of the curve is exactly for the Jacobian of the curve is equal to this polynomial. So, using again the Weil theorem for hypothesis Riemann for the curves of a finite field, we can see that the M belongs to this set. And if we want to consider the number of rational points of the Jacobian of the curve over Fp, mod 4, we can see that it's equal 2 plus M. And okay, we need to show that the M is 0. But how we can to do this? We use some property of some two-decent computation for hyperpletic curve. And two-decent, I mean counting the number of order 2 and 4 in Jacobian of the curve over Fp. And using some two-decent computation, we can see that the M is exactly 0. Does that mean L polynomial of the curve is exactly equal 1 plus Pg 2G over Fp? And using the property of L polynomial, we can see the L polynomial of the curve over Fp2G is exactly having this form. Is that mean the curve is maximal over Fpg? Thank you.
Okay, thank you, Said, for the talk. Do we have any questions?
You say you did not know whether those curves are covered by the Hermitian curve?
The first one, in the case of the P is -1 mod 4.
You know that.
Yeah, yeah.
What about those?
Yeah.
The last.
Yeah, because X also is covered by the Hermitian curve, and you know that
This one is covered by the emission
no,
curve?
I mean,
No, I'm
depend
asking
on
if
the
you
P.
know the last one.
No, exactly, is our question also. But I think.
Do you know? I mean, you have a guess? You think it's?
I mean, the guess is not covered by Hermitian because it's a depend of the L. I mean, depend of the if it's covered, it's not. It cannot be depend of the property of L. Is it some? I mean, the guess.
Have you tried example?
Unfortunately, we couldn't find. I mean, it's that is not, because the genus of this curve is small and is difficult to verify that this curve can be covered or not. So it's difficult. Thank you.
More questions? Okay, if not, let's thank the speaker again.
Thank you.
Okay, so our last speaker of the day is João Paulo Guardiero from University of Campinas, and he's going to talk about Tate Shafaverich results for quartic twists in characteristic 2.
Thank you, Lucas, and I would like to first thank everybody from who made this conference possible, everybody from the organizing committee, from the scientific committee, from Setor de Eventos, and the guys from Audiovisual. Thank you, Paulinho. Thank you, everybody. And, also thank you, Said, for helping me on the introduction of some of the topics that will appear here. Because, I will talk about one of the problems that I studied on my PhD, which is Tate-Shavarovich results for quartic twists. So here we have two, let's say, names that some of you might know, some of you might not. But at some point, I will, let's say, translate this title. So I hope that everybody can get, well, at least an intuition on what's happening here. And, well, the basic object that I worked on is elliptic curves. So an elliptic curve for us is any genus 1 curve defined over some field K with at least one rational point. So when we talk about an elliptic curve, you need to fix three things. You need to fix an equation, which gives you a genus 1 curve. You need to fix a field, and you need to fix a point. So, okay, we know that this curve has at least one point. But how many are there, and how are they? How are they distributed, let's say? So at first, Mordell showed that if the base field is Q, the field of the rational, then the set of Q rational points form a group, and even more, a finitely generated abelian group. This result was then generalized by Weil and then Lang and Heron. And this is, let's say, one of the most recent versions that we have. So this result holds for any global field K. There is a function field over a algebraically closed field or a number field. So what does this say? That the set of K rational points is some finite torsion subgroup and R copies of C. And in this problem, we are interested on R. One natural question is, what is R? How large can it be? Can it be arbitrarily large? Is it bounded? Well, let's focus on the function fields case. For K equals C of T, this is still an open problem. If I'm not wrong, the current record is due to Shoda, which is 68. But for function fields of positive characteristic, the answer is yes. So first, Tate and Shavarovich showed a way to construct families of elliptic curves having this property of arbitrarily large R. And around 20 years later, Elkis did the same thing for fields of even characteristic. And what do these two papers have in common? They used the quadratic twist of some supersingular elliptic curve. And well, what we did on this part of my PhD was to obtain, like Elkis, new families of elliptic curves having this property of arbitrarily large rank, but now using a quartic twist instead of a quadratic one. And well, to do that, we studied the group of morphism from a Jacobian variety to the elliptic curve. And Jacobian variety is what Said told us. Well, in this talk, I will not go deep into the method, but I want to present the rank formula for this Mordell rank. And why is this work relevant? Well, this is a new method for constructing elliptic curves with high rank. Also, since we are using quartic twists and many algebraic curves while doing this research, we saw some developments on their theory. So, for example, so far we had not seen any expression for a quartic twist in characteristic 2. So there might be some, but we did not see yet. So this might be one of the, let's say, first expressions. And also many applications to the theory of error correcting codes and Mordell lattices. Okay, so let's go and translate the title. We have two main concepts here, the quartic twists and Tate-Shavarovich results. So for us, well, a quartic twist, you start from some elliptic curve E, defined over some field K. And a quartic twist is any other elliptic curve E prime, also defined over K, such that these two curves are isomorphic, but not here. The isomorphism cannot be defined over K. It should be defined over some degree 4 extension. So you have the isomorphism here. This is why we call it quartic, because we have to go to a degree 4 extension. And also the results from Tate and Shavarovich. I should say that this is not the precise statement of their result. This is just some rewriting for our case, which is what we really use it for the rank formula. So you start from some elliptic curve E and any algebraic curve C, both defined over Fq. Well, you denote by Fq(c) the function field of C. This is a field, so you can ask, how is the behavior of the Mordell-Weil rank of the Fq(c) rational points of E? And the results from Tate-Shafarevich tell us that this rank is given by some exponent that appears on the numerator of the zeta function of E and C. So you decompose the numerator of the zeta function of C as some exponent of the numerator of the zeta function of E times some remaining polynomial. And, well, the rank is given by this exponent here. Okay, so in order to construct our rank formula, we used the method developed by Sven Botsma, Said Tafazolian, and Jaap Top. And this method consists of first considering a cyclic extension of Fq of t, the function field of P1. But this cyclic extension must be related to some maximal curve. And then you obtain the twist of some, let's say, well-behaved elliptic curve, construct a vector space from it, study the eigenvalues, and, well, the dimension of these eigenspaces will be given in terms of the Mordell-Weil rank of some elliptic curves. So you use Tate and Shafarevich results to obtain the dimension of the eigenspaces, and via this you obtain the rank formula. So in our, the difference from their method to the one that we used on this project is that first we replaced Fq of t by any function field of some curve x. So not only, let's say, the function field of P1, but the function field of any curve. We dropped this maximality condition, although in our examples we had to take it back. And we considered quartic twists in characteristic 2 instead of the twists they used on their work. Okay, so now in our case, which are the main characters of our work? This is the well-behaved elliptic curve. It is supersingular. It is defined over some extension of F16. This F16 is really important for one of the eigenspaces. In order to obtain its dimension, we had to consider some isomorphism between it and another elliptic curve, and this isomorphism is defined over F16. That's why we need this restriction here. And, okay, we start from some curve C, also defined over some extension of F16. And this curve C must have a order 4 morphism. We now construct two curves from C and sigma. First, X will be the quotient of C by sigma, and H the quotient of C by sigma squared. So C can be seen as a cyclic degree 4 extension of X, and H can be seen as a cyclic degree 2 extension of X. So if we recall that the characteristic of the field is 2, then using Artin-Schreier theory, we know that X is some Artin-Schreier extension of X, the function field of H, sorry, is some Artin-Schreier extension of the function field of X. So let's say H is R squared plus R equals A for some A here. And C is a double Artin-Schreier extension of X, and let's say Artin-Schreier extension of H. And using C and sigma and this E, we could find a quartic twist of E defined over Fq of C, which is given by this equation here. So another supersingular elliptic curve, of course, eta squared plus eta equals this guy here. The coefficients are in the function field of X. So E and EAB are are quartic twists in this field here. And the quartic thing is that we use both R and S. So in this, the isomorphism between E and EAB should go up to Fq of C, so we can find the isomorphism. So it is indeed a quartic twist. And now for the rank formula, I'll just use one of the theorems that Said showed us. So the numerator of this elliptic curve, the numerator of the zeta function of this elliptic curve is this guy here. So E is either maximal or minimal, depending on M being odd or even. And we write the numerator of the zeta functions h and c as these guys. So you decompose as some power of LE, and the Mordell-Weil rank of this group here, the f of x rational points of EAB, is twice the exponent of c minus exponent of h. But yeah, using zeta functions is really hard. You saw a lot on this week. So we can look into a more particular case when C is a maximal curve. If C is a maximal curve, just like Said said, H will also be a maximal curve since C covers H. And then you can change this M by the genus. And this is way easier to compute. So to find examples, we use the corollary and not the theorem in its full strength. So the first example, let M be an odd number. This curve here is maximal over some extension of F16. This curve was studied by van der Heer, van der Vlucht. So the reason why this is maximal can be found on their article. And for any C satisfying this trace condition, there exists some polynomial B, which can be explicitly constructed using C, such that this guy here, the E T over C square B, has this rank, 2 to M over F2 for M of T. So the Mordell-Weil rank of the elliptic curve, the quartic twist, is, let's say, the square root of the cardinality of the field. Ignore the T. So yeah, we could obtain our goal, because if you give me some number, I can give you some odd number M, such that 2 to M is greater than this number. So we proved that the Mordell-Weil rank cannot be uniformly bounded. And another example using now the trace function. So you start from some odd degree extension of F2. TR is the trace function from F2 to FQ to F2, sorry. And this curve here has rank Q over FQ4. So the Mordell-Weil rank is the fourth root of the cardinality of the field. And now what do these two examples have in common? Well, there are some maximal curves involved here. If you read the proof of this example, we use some maximal curve as well. And the curve H is P1 again. So yes, we have some quartic twist, but in some sense we are still looking for quadratic extensions. So my PhD ended, and now one of my postdoc problems is to continue studying these curves here. We would like to study and maybe obtain the zeta function of C. So, well, maybe not on the full generality of C, but some examples that we might find, let's say, non-trivial examples for our theory. So H does not need to be P1, and C do not need to be maximal when H is not P1, if it exists. We don't even know if there's some maximal C when H is not P1. And how to do that, I don't know. So that's why I wanted to present this work here. If anyone has some hint on how to address this problem, you can email me, you can, well, talk to me. And if you want to see this paper, you can find it already on arXiv or on JAA. Well, it is to appear next year, but it's already online. Thank you very much. Yeah.
Thank you, João. Do we have any questions?
You talked about Tate Shafarevich. I was curious if you're going to say something about the Tate Shafarevich.
I don't know what a Tate Shafarevich group is. I did not study this theory, but I know it's a very, very important thing. But we were only using their construction, let's say. To be honest, this work, here.
You have the formula for the L function, right?
Yes, for the elliptic curve, yes. Mm-hmm. Okay. Yeah, I was going to say that this result here is actually a corollary of some work of only Tate. The Tate Shafarevich thing is when they used this result to construct the example. So, thank you.
More questions? Okay, if not, let's thank the speaker again.